help welcome Brian, please.
Thank you. So like I said, I started an aerospace company. I'm Brian Stofiel, head CEO, chief engineer, CFO. That may all sound impressive. It means there's nobody else to do the job. Started the company about 2 years ago as a company. And I hired U.S. military veterans mainly because they ask, how are we going to do it? Not if it's possible, how are we going to do it? And that's a big thing when you're starting something brand new. I'm going to give you a quick layout of what we're doing, and then we're gonna have a little talk. So this is the same speech I gave at ISDC recently here at Union Station to the space industry. We're classified as a small satellite launch system, so that's under about 800 pounds. Our payloads are smaller than 800 pounds. Most of them end up being about 30 to 40 pounds and about the size of a toaster. So a lot of the schools are starting to put these up. They're called CubeSats. A 1 unit CubeSat is this big. So you just keep adding units and there you go. It's a standardized size. There's about 280 in qualifications. There's 2,000 under development. We predict in the next probably 10 years, 5 to 10 years, there'll be 10,000 of them on the ground waiting for launchers. Okay? And these go everything from grade schools putting up little experiments to big corporations actually doing experiments for biology, for crystal growth, for engineering, and then of course imaging. Imaging is always the big one, looking back at Earth, looking up at the sky. That's most of our commercial market. We are a commercial launch system. We are not NASA, we're not government, we're here to make a profit. Around the world, there's about 112 small satellite launch systems under development. Most of them are on the drawing board. They're out there trying to troll for cash, as I like to say, trying to bring up that capital. We took a much different approach. We bootstrap, which means I've got a day job that I pay for everything. Everybody on my team pays for everything. The advantage is we get to choose the direction. We can take the projects we want to take. We turn down a military to build a weapon because we will not build weapons. We will weaponize, but we don't build weapons. It takes away from our space program. So last year they launched about 200 of these, about 300 of these small satellites. What we have is called Boreas. We take our rocket, we put it on a weather balloon, we send the weather balloon to 100,000 feet, we're on the edge of the atmosphere, and we launch the rocket from there. Less engineering, because I don't have all that air I have to go through. There's less propellant, it's easier to control, and we're only operating outside the atmosphere in the almost vacuum of space. Makes us light, cheap, and easy to build. The big thing that's unique is we don't have a liquid engine. We are solid rocket only, okay? And that means that a normal solid rocket, once you light it, you can't stop it. It just burns. So you can't do accurate orbits because you can't change your thrust, right? Okay, if you're going too fast, you need to be able to slow down. Otherwise, you're gonna shoot over your target. So we're developing a way to actually utilize these solid rockets. Single payload profitability, which means we can put one satellite on our rocket and fire it. Most launch systems right now, you have to put a bunch of satellites on the rocket, fill up its weight capacity, it's what we call lift capacity, to make it profitable. We're able to make it, because of the solid rocket, profitable at one payload. Right now, these small satellites are waiting 2 to 4 years to get into orbit. So you may have your satellite finished as a grad student, and it may take 4 years to put it in orbit. Our system, we want to fire 1,000 missions our first year. There hasn't been 1,000 space missions in the history of mankind in a year. But we think we can do it with this system just for mass production. So these are some of the static fire tests. The Mark 1 is up in the upper right-hand corner. The middle one's the Mark 2, and the bottom one's the Mark 3. We've developed a quick process. This is a 3D printed piece of plastic. You ready? These are what we actually fire. What we do is that right there cost me about $1 to make. And these 3D printers, you take an image inside your computer and you basically are printing it out in layers on plastic. Well, we heat treat it and then we fire live rockets. Those are pieces of plastic. They melt at 200 degrees. We're bringing them up now to about 2200 degrees with off-the-shelf stuff. I went down to the hardware store, picked up stuff off the shelf, walked into my grandmother's basement and started building. Okay, it's that type of thing. This technology, the kids, I want to tell you right now, because you guys are my market, you guys are my customers. I'm not really talking to these adults. By the time you guys get into grad school or into college, this system will be running, and you're going to understand it better than I do. Okay, this has all of human knowledge on it. All of human knowledge is on this device. Okay, if you want to know something, go pick it up and read it. Okay, I'm not an educated PhD yet. I'm in my PhD program at SLU. I started this company not knowing anything, and I went out to the MIT lectures and got them offline and listened to them. I went to this NASA and got their lectures, and I basically self-taught myself a lot of the rocket science that I'm doing. You don't need to wait for your teachers. In fact, in my opinion, they're holding you back. There's a lot out there. My daughter's been doing 3D printing rockets, drones, since she was 5. And the story I'd like to tell is we were at the RNC because my office was a mile away, and it's a good way to hit the politicians. And I taught her to use lapel pins to identify senators and congressmen. Well, one of the congressmen asked her, well, what do you want to be when you grow up? She goes, I want to be a biological engineer. And she wants to engineer biology, right? Make her own stuff. And he goes, well, you're in the space industry. Why aren't you going to space? She goes, yeah, but that's just where I do my job. She literally does not see astronaut as a job because of the way she's been brought up in the industry. And I don't think you kids are going to see that either. Okay, because you've got to be an engineer to go to space. You've got to be a biologist to go to space. Astronaut is no longer just a job. It's what you're going to do with it. So these rocket nozzles cost me a couple bucks to make, probably another $50 to heat coat and treat and put an engine in it, $100 to put an engine in it. The printer these come off of is a $150 printer. It's a $150 3D printer. This is not a $3,000, this is not a $20,000 3D printer. $150 3D printer. The technology is changing so quickly that later when we get into our development, I think the optimal engineering team is a brand new engineering student and the most experienced engineer. Brand new engineering student understands this technology, whatever it is, the computers, the microprocessors, the 3D printers, just the apps that you guys use. And then the experienced guy can guide that. The technology is changing so quickly that the aerospace industry is about to change. You're going to have hypersonic flight from here to Sydney, Australia in 2 hours, and it's going to be cheaper than a current airline ticket. The aircraft are cheaper to produce, they're cheaper to run, they're cheaper to maintain. And that's what's about to happen. The microprocessors, everything that happened in computers and cell phones 10 years ago, 20 years ago, is hitting the aerospace industry. I think it's a quarter of SpaceX's engine is 3D printed in metal. So this is not something that we're talking about in 10 years, this is now. We've been firing these for over a year. We've fired 21 to date, we've test flight 3. In the next 7 weeks when my daughter gets here, we're gonna fire between 30 and 50 of these, okay? And that's a good series. That's just the Mark III series. We'll go to the Mark IV and the Mark V and the Mark VI. So this 3D printing process is pretty cool. Here's some more pictures. I've changed some of the colors. There's some different angles, the upper left and the mid left. Those are the same engine at the same time, or very roughly the same time. And you can see that shock wave developing in 2 different videos. Those pictures came off of GoPro cameras. Okay? $100, $200 GoPro camera. This is not high-speed infrared. This is, hey, I can go out in my backyard and fire that rocket. Okay, and I did. The neighborhood kids, that one on the left was actually built by 2 of the neighborhood kids in Akron, Ohio, and my daughter. I taught them to 3D print, and then we used epoxy to epoxy it together, and then we spray painted it with the heat coating. It's 2 different types of heat coating, so it's a regular type of spray paint and a graphite held in alcohol. So it gave them that type of feel, and they built them and we fired them. It's not hard, it's very complex. And if you have somebody that help you with that complexity, okay, this stuff isn't hard. We know how to do it. I actually have right here the signatures from the old Mac team, the old Mac's old team. These guys built Mercury and Gemini, okay, before we understood what space was. Okay, we didn't know what space was. They didn't know if they were going to land on the moon and fall straight through it. They didn't know if they'd get up there and the person blow up in the ship. Nobody had ever done it. One of the stories they tell is they're out on a Redstone rocket at the first group that went out to Cape Canaveral, and they've got a fully fueled rocket out on the pad. And here comes a lightning storm. And that thing's a giant lightning rod, right? Full of explosives. The word comes down to run away from that thing. Because if it's going to get hit, it's going up. The thing with the space program is we don't care if you blow up equipment. Don't hurt anyone. That's the general rule. NASA for years has always had a zero loss policy. The losses that they take they've done everything they can. And even the space industry, we always say they've always done everything they could. So we came out of Cleveland, Ohio. Sorry about that. We came out of Cleveland, Ohio, Kent State University, and are going to be here at SLU. If you don't know, SLU's got an amazing space program. CubeSats, they've got a rocket team, everything. But where are we going to go? So Boreas is our way to profitability. That's how we're going to make our money. Okay, we're going to be that on-demand. You call us, we go out to the parking lot out here and launch a balloon, and you got a rocket in orbit in 2 hours. Okay. Small satellite, this wing you see is our small satellite re-entry vehicle. The biological experiments and the crystal growing, the pharmaceuticals, they like to get their experiments back immediately. Because the longer it sits inside gravity, the more it affects it. So this would actually fly to, let's say Monsanto needed it, we'd fly it straight down to Lambert after it came out of orbit. It also sits below our balloon as our command module. We see it also as a planetary return system. You go to Mars, we want to send you guys to Mars. You want to send a rock home? You can't just put it in the mail, right? So you 3D print this system on site, and then you put your sample and you return it home. The only thing you're carrying is the chemicals for the rocket cartridges and the electronics. That's easier to carry than huge amounts of rocketry. Very simple system. We are looking at the asteroid belt. We don't particularly care for Mars. We're looking at the asteroid belt because if we can do a geological sweep of the asteroid belt, we can sell that to every miner out there. They're going to want to know all that data. And we call that generational data. It'll basically support the company over a generation because they're just going to be coming to you on a constant basis. It's not a bad mission. 6 to 9 satellites can actually do most of the belt within about 3 to 5 years. And then human spaceflight. You guys want to build your own spacecraft. That's what this is about, right? Well, my retirement plan is I want to build a spacecraft of my own. I want to take it to a destination of my choice, and I want to live my life out around that destination. So I'm actually looking at the Saturn system. Titan is probably one of the most interesting moons out there. It's got over 120 to 150 different hydrocarbons on the planet. This isn't just methane, this is raw crude oil. This is all the biological hydrocarbons. So the current philosophy, either there was a ton of life on that planet, or we've discovered a new process to produce hydrocarbons. I always pronounce this name the new water world, or the water world around Saturn, is the most likely candidate for life. It's just like Europa. Enceladus is the name. It's just like Europa, except they did the math on the energy being produced by the planet into the ocean, and it's warm enough, and there's enough energy for complex life to form. So it's one of the more likely candidates there. And the Saturn system's very interesting. It's low radiation compared to Jupiter. Jupiter might be interesting, but it's a hostile environment, which is the same reason I don't particularly like Mars. There's no magnetic field, which means all that solar radiation comes right down to the surface. The joke I make is Elon Musk is actually, that boring machine he's making is because he knows you have to live underground on Mars. Okay, so he's planning on tunneling on Mars. What I got up here is I've got, and you guys can come play with any of the 3D prints up here afterwards, okay? But this is something that's really pretty cool. This is the Copernicus crater on Mars, or on the moon, okay? And this is actual NASA data. So we downloaded the data and then turned it into a topographical map. And like I said, you can play with these, you can press on them, I don't care. You can't break them. I print another one. This is less than $1 worth of material, okay? This is another region on Mars. This is a exaggerated globe of Mars, so you can see the mount and everything like that. Here's the actual valley. That valley is 3 miles deep. To give you an idea, the Grand Canyon's about a mile. And it stretches 3/4 of the planet, or a quarter of the planet. And you can see that on the globe. What this 3D printing, and this is what I'm talking to the kids about, you kids, is you want to take an idea. The greatest thing about being an engineer is I can make something up in my head, draw it out on paper, put it in the computer, and within about a day or two, have a brand new piece of plastic like this, okay, or like this nozzle. Okay, you're no longer waiting months to see your ideas come out anymore. Even when you're computer programming a game, you can't produce something that real, okay? These two, you ready? Whoop. Squeeze them. Squeeze it, I mean, like crush it. That is some flexible plastic. The materials you see, the hard plastics, you don't have to do hard plastics. You can do these flexible plastics, you can do these different clear plastics, you can do glass, you can do wood, there's metal. So these are what you guys are going to be using, right? You know, this is what you guys are able to use. And your parents don't understand it yet. I moved in with my 90-year-old grandmother 8 months ago. She passed away 2 weeks ago. But what I learned, one of the biggest things, is I introduced Alexa into the house, which is one of the okay? She's 90 years old, drove every day, went to bridge 4 times a week, you know, the whole 9 yards, was a Spitfire. She told me, she goes, I don't see a use in the technology. I brought the Alexa in, and then I started showing her, my aunt was in Greece, and we did a video chat. And after about a week of using this stuff, she looked at me and goes, now I understand. But at the same time, it showed me that it wasn't just that you didn't see the use in it. We make toys with these 3D printers, right? Every one of these rocket nozzles saved me $10,000. To do this out of metal would have been about $10,000, okay? To do it out of plastic, that's about $5. Okay, so when somebody tells you you don't have the money to do it, you find a different way. You got $20 million? Because I'll get you right up here. The software that's out there, there's all the model rocket stuff. You can model on the software now, open source. It's called Open Rocket. There's a couple different programs out there. So you can model your little rocket that you got up at Michael's. You can put different engines in it and do the computer simulation. Okay? And it's so simple. I'm telling you, you kids out there, go try it. You'll have it in 10 minutes. We can't model our rocket simulation. We can't model the flow going on inside of it. It's part of the problems we have. So the reason we have to do these experiments is we have to get our data points. And I have to run a lot of them, okay? So there's a reason we went with the cheapest, most inexpensive plastic we could find and easiest to use. And that's what I'm trying to get across to you kids is, look, you don't need millions of dollars. This would have cost me $10,000, it cost me $5. I got the ideas from the hardware store. Okay, we used to call this, back in my day, which was the 1990s, right? We used to call it hacking. You take a material and hacking. You still hear this term, but I hate the term because it's not. You're taking the materials and you're using it, okay? My heat coating, the industry's trying to figure out how we're doing it, and I'm buying it from Home Depot and AutoZone, okay? It's not a hidden secret. There's a gentleman, he's a high schooler. He's building rockets on his own and guidance systems. He's more interested in actually guidance systems, which is the computer side. There's kids out there in India, they're building big rockets, stuff to lift 50 pounds and 60 pounds to put a rover on the moon. Space is not in the future anymore. The commercial industry is about to give you guys access at very low rates. Our rocket system, we'd like to actually get to about $300 a pound. So for every pound, it would be $300 to orbit. Right now, they're sitting somewhere around the $8,000 mark a pound. That's why nobody's going to the moon. That's why nobody's leaving low Earth orbit. Because you're too interested in The Walking Dead. But this is one of the space industry memes that is out there is the cost of the Curiosity rover was 1/10 of what was spent on the movie Avatar. Okay, and that rover's been on that planet how long now? Cassini's been around Saturn. It was considered one of the most expensive space missions, but it's been around Saturn for 13 years, giving us data. If you guys don't know, in September it's going to crash into Saturn. They've been passing between Saturn and the rings, and they'll continue to do that until August, September, and then they'll deorbit it into the planet. And that's done purposefully to destroy the probe, because we don't want to litter the universe. In fact, the big question about Mars is it really a dead planet? Or is there life there? Is that life something that we're going to squash? Or as the xenomorph facehugger, are we going to roast it on the open fire and eat them? Okay, have you ever thought about that? Are you going to eat an alien if you meet one? Because we tend to do it, right? They're going to eat you. I mean, we always see in Star Wars and Star Trek all the sentient, but you don't think about that every now and then. You're going to have to start thinking about that. I mean, if that is a water world on Europa or Enceladus, what is our responsibility to it? Or if Mars is completely dead, if there's nothing on there, what is the responsibility? Can we nuke it to terraform? You nuke the poles, you boil off that carbon dioxide, and now you got an atmosphere. These are the questions that you kids are going to have to deal with. We can all speculate on them, but you got a real problem. If I go out and grab an asteroid, one passed between the moon and the Earth 2 Halloweens ago, had more platinum on that asteroid than on the whole Earth. Okay, passed between the Earth and the moon. If you had captured that asteroid, you would have destroyed the economic platinum market. You would have crashed the market. So what is the responsibility to the economy? If you grabbed that asteroid and brought it back down here, you would flood the market with cheap platinum. So that's the type of thing. We get into the environmentals on this too. The only way you're going to save this planet is to get humanity off its resources. And that means getting us off this planet. The analogy I use is if you stayed at home and never went anywhere, you just stayed in your house all day, okay? You'd pollute the place, you'd starve to death. No matter how much you ration, no matter how much you try to get rid of it, you're in one place. It's a finite space. It doesn't get bigger. So space is like our local neighborhood. We can go out there, we can get resources. Yes, the distances are difficult, but they're out there and they're just out there sitting there. And most of the time in raw forms that we can get to easily. But at the same time, you've got to leave this Earth. Okay? You could turn it into a nature preserve for all I care. Okay? The whole Earth. Okay? But as long as you're here, you cannot recycle and conserve your way out of killing yourselves. And that's what humanity will do. And I'm talking to you kids. Okay? You want humanity to survive, we have to go to space. Okay? Otherwise, you're going to eat the planet up. And we don't want to do that. It's a nice planet. I've traveled, 13 countries, 46 states. And I travel as much as I can. I hike as much as I can. I love this planet. But we need to get off of it. We're killing it that way. So when we have these ethical discussions about, is Mars really a dead planet? Or is the moon really somebody's property? Okay, it's a big discussion. And you kids are going to have to deal with it. Right now, I cannot deal with foreign nationals. Anybody outside the US as a launch system, any of the launch systems, we will not deal with foreign nationals. So you have a payload outside the US, I can't touch it. And that's a leftover from the Cold War. Okay? So the Indian space program we really can't talk to as a commercial entity. These are some of those issues. The system we're building is a ballistic missile. It's an ICBM. It's a delivery system. It's a deorbiting system. To give you an idea, if you brought something down on New York City from 17,000 miles an hour, it would be a nuclear weapon with no fallout. So when we're talking about a lot of energy, when we're talking about these ethical things, there's some serious ethical issues. I can't just sell you a rocket so you can put it in orbit because somebody's going to weaponize it. If I had the ability to give you a nuclear reactor that would power, is completely safe if you left it alone, and it would power your whole house, I couldn't give it to everyone because somebody would weaponize it. You know, there's a lot of kids here, and there's one of my engineering idols I always bring up, Browning. 100 years after his designs were made and created, they're still a standard, and they're still the best on the market. Okay? As an engineer, that's a great achievement. But it's also a design that hasn't changed in 200 years, and it's 2,000 years old in its propellants. If I pulled out that invention, everybody'd freak out. If I brought up here a ballistic missile and set it down on the table, you'd be all of you would be up here touching it. An armed ballistic missile, and you'd all be up here touching it. My pistol, you would be all afraid of. The pistol can hurt one person, 2 people, dozen people. That missile can wipe out millions. But yet you're afraid of the pistol and not the missile. So there's a dichotomy that you kids are going to have to learn about where these ethical questions are really going. Do we wipe out a microbe on Mars because it's the only microbe on Mars? It's only one, and we want to terraform Mars. Or do we capture that and use it for our methods? There's some big questions. Do we wipe out an economic structure because we want to bring back a large diamond the size of New York, right? A chunk of gold, the size of the moon. These things exist in everything. Yeah.
I was wondering if you could talk a little bit more about the Asteroid Belt geologics.
Okay.
So because that's part of what they're interested in, right? Is looking
Yes.
at asteroids for, the rare
So all your green technologies use neodymium magnets, or these rare earth magnets. 90% of your supply currently comes out of China, and it's a total environmental disaster. And that's one of the main reasons they want to go to the asteroid belt, is those rare earth magnets are incredibly useful. Everything you own has got something in it, all your computers, all your cell phones. There are also chemicals that we know of that are pretty common, like helium-3. Helium-3 is a great propellant. It's a great chemical. It's a great compound, but there's none of it on Earth. Okay, the moon's got tons of it. It sits in the regolith. It's really easy to process out. So the asteroid belt and the resources that are available in space, I'm going to stress this a little bit more, are literally infinite. They never end. You can't use them up. You will keep going forever. So when you go to an ethical decision of, am I going to mine an asteroid? Well, what is it going to do? What's the damage it's going to cause? So the resources that are out there, part of what we see is you don't even know what is on those asteroids. So even if I go buy it with a scanner and scan it, okay, we may come out with compounds that we don't understand. And these compounds may be the best compounds we've ever discovered, but we don't even know they're there. People say exploration doesn't give you anything. No, it's probably a 4-to-1 return on exploration, because finding out something new is what spawns that innovations. Silicon, I mean, the nuclear industry, everything was spawned on by somebody looking at something and seeing something new about it. Our system alone, solid rocket engines. Everybody knows you can't throttle a solid rocket engine. Everybody knows you can't put 2,000 degrees through a piece of plastic that melts at 200 degrees. But we do it. Okay? When you get out to the asteroid belt, it is huge. The expanses are giant, and there's an energy problem everywhere. Just like your batteries on your cell phones, space energy is the problem. If we want to go fast, it means we have to carry a lot of propellant, and then it runs out. Getting out to the asteroid belt requires going fast in any amount of time. Once you get there, you got to slow back down. More propellant. Okay? If you want to move that asteroid, more propellant. And that propellant, just think about your battery on your phone. That's basically what propellant is. Once the juice is gone, though, you can't put it back in. So you've probably heard about the electric engines that are coming out. The microwave engines are trying to take and remove the propellant out of the equation so that we can get to those asteroids. And there's everything from what you would think of as like sedimentary rock all the way up to ones that are pure metal. Can you imagine landing on a pure metal asteroid? I mean, just trying to mine the thing of iron ferrite. And there's a lot out there. Now, you guys have probably all seen in Star Wars the asteroids banging into each other. You're flying through an asteroid belt, right? That doesn't happen. Okay, those asteroids are tens of thousands of kilometers away from each other. If they were banging into each other all the time like that, and it was a dangerous place to be, they'd be in dust. They wouldn't be big chunks of rock because they'd be hitting each other all the time. So most of these asteroids are actually in stable places. They've cataloged a lot of them, and they're cataloged in general type catalogs, but we don't actually know what the type is. We're doing a good example is spectral analysis. We take the light reflected off an asteroid, we break it out into the rainbow, and then determining what parts of the rainbow are the brightest is how we can tell what elements are in that type of asteroid or in that type of body. So just by looking at the light, we can actually tell what the asteroid is made out of without having to go close to it. And that's how we tell stars and that type of thing also. What's your question?
I had a question about the asteroids hitting each other.
Yep.
What about the asteroid that hit Earth? It's not that same.
Asteroids hit a lot of things.
That was a chunk of an asteroid that was made when two asteroids collided.
Everybody, you know, these are all craters, right? This is an asteroid hitting
a body. And a body can be anything. It could be the spacecraft. The ISS took a piece of paint chip. It hit the cupola, which is a viewing platform. They can look out all these windows in 360. This paint chip hit the cupola window and put a crack in it. A paint chip, because of the velocities it was going, how fast it was going. Okay, it doesn't have to be big to hurt. That paint chip would have gone straight through you, right, if it had hit you. So asteroids hitting things hit things all the time. You guys probably don't remember the comet that hit Jupiter, Shoemaker, left huge scars across Jupiter, but they only lasted about a month or so, and then they went away. Planets, nature are very resilient. Humanity, life is a little less so. That's why when you wipe out dinosaurs, right? Well, here's an interesting thing they've told us. They found the cold virus and blue-green algae living on the outside of the space station, living in deep space. The cold virus lives in deep space. Blue-green algae lives in deep space. So the going theory with me is life's pretty prolific at the primitive form. If those things can survive in deep space, which is one of the most hostile environments, when you're in the sun, you're at 245 degrees plus, and when you're in the shade, you're at negative 245 degrees. So if you stood there with sun on one side and you on the other, one side of you would be burning up, the other side would be freezing cold. Think about that with a spacecraft. Apollo always rotated, and it was like being on a spit. Like you had a pig on a spit, right? And that's how they kept that heating from overheating the spacecraft. Engineering in space is completely different than on Earth. Water doesn't rise to the top when it's heated. There's no convection, right? Warm air doesn't rise, cold doesn't sink, because there's no gravity. So when you go to boil water, everything next to the heating element turns to vapor and displaces the rest of the water. You never get convection that occurs. You guys heard Apollo 13, we're going to turn on the stirrers in the tank, okay, in the oxygen tank. That's to stir the tank to get convection in that tank so that when they heat it, they don't just heat what's next to the heating element. So just boiling water in space is a completely different experience. The space shuttle's main doors flex 6 feet in either direction so that they would shut because of that uneven heating issue. You couldn't stay in space if you couldn't open the doors, and you couldn't come home if you couldn't close them. So they had to close and open. So they made them so they flexed 8 feet in either direction or 6 feet in either direction. Yes?
You said we might have to leave the Earth. Like, how soon do you think we would have to leave?
I don't put time scales. Eventually. The sooner the better is probably, and if you guys didn't hear him, he was asking for a time scale on how quickly we'd have to leave the Earth. Alarmists, you got problems. Okay, there's some serious problems, but alarmists, I think, are a detriment to what we're actually doing. We need to do this in a long-term basis because life, here's a great reason. If we're the only life in the universe, what is our responsibility to spread that life? If the Earth is the only place where there's any type of life in the universe, what is our responsibility to spread that? If we're not alone, what is our responsibility to spread our type of life? Okay, these are big ethical questions, little guys, that you're bringing up, right? Okay, you know, what if we're the only ones? That means we really need to get off here so that life continues, so that asteroid doesn't come in and wipe us out, right? Or wipe out the whole planet, not just us, most of the life. But we're finding life everywhere, right? I mean, we're finding it where we don't expect it to be. So volcanoes, you can find sharks going through volcanoes. You find cuddly bears is all I can think of. They're little microbe guys that will literally freeze dry themselves. They can live almost anywhere.
There's a whole classification of animals that are that. Teratins, I think is what they're called. But yeah, these extremes. Yeah, what you got?
How big can an asteroid get? Or how big has they been reported?
This goes to that Pluto question. It depends on what you classify an asteroid as. Because if it's free floating and not in orbits or it's not around a planet, it could be huge. But you could also talk about it being a moon or it being a planet. You know, Sirius and Vesta are two Plutoids inside the asteroid belt. They're a subclass of asteroid that are subclass of planet. And that's what they did to Pluto, right? They took it out. And one of the reasons they did that is there's about 12 other objects that are bigger than Pluto out there. So they would have had to add these other objects just to keep Pluto as a planet. And now you'd have 16 or 20 planets in the system. And those 12 objects we don't know a lot about. I mean, we just don't know where they're at. They're so far out there, they're so extremely out there, and they're on weird orbits that we just don't have the ability to look at them. So that's one of the reasons they took Pluto out. Is nobody really knows where the classification. It's an arbitrary line that scientists make. We try to attach characteristics, but it's still an arbitrary line. Yes?
When you put your science experiment in outer space, you have it attached to one of these rockets like this? And then how do you recover them? And do you have remote controls on them so you'll know when to blast? And do you use gunpowder or?
Gunpowder won't burn in space. It needs an oxidizer. So we use a composite rocketry that includes an oxidizer. It includes oxygen in the fuel. Okay, because you can't fire gunfire. What we use, this wing you're seeing here is actually, we would put the payload or the small satellite experiment in there and fly the whole wing into space with the rocket underneath it, and then fly the wing home. Most of these satellites are not recovered. In the weight class we are, they go up for a couple months, you get your data downlinked off, and then they burn up in the atmosphere. Yeah. My system, even the rocket system itself, is designed to burn up in the atmosphere. We are not reusable. At this weight class, we do not see a profitability in reusability. You're talking about an 800-pound satellite. Satellite probably doesn't cost more than $1 million. Just one of the engines on one of these big rockets can cost over $1 million. That's why they're trying to reuse them, is because that liquid engine is very, very expensive to make. And as soon as you make it, it starts to deteriorate, which means if you don't fly it immediately, it may not work. Solid rockets, we can set them on the shelf for 10 years, pull it off, and it'll fire like we built it. Very proven technology. But that's why they want to go reusable.
Are you concerned that launching tens of thousands of small satellites will pollute the low Earth orbit and they will never be able to
Nope.
leave the planet anymore?
Nope. Nope. And you want to know why?
Why?
Mine fall out of the atmosphere, fall out of the sky in under 2 weeks. He was talking about space debris and launching thousands of small satellites into low Earth orbit. We don't worry about it because we are in real low Earth orbit, which means that we don't have propulsion systems. We can't, eventually gravity drags you home.
And how long does it take?
Anywhere from 2 weeks to about 4 months. So you're really talking real short-term durations. The event you're talking about is a Kessler event, and that's what you saw in Gravity. If you guys saw the movie Gravity, where one satellite hits another satellite, and then it hits another satellite, and now you got space debris, and you've got a cloud of debris around the planet that you can't leave the planet anymore. You're stuck on Earth. Okay, and that's what they're worried about with space debris, is this planetary cloud. Low Earth orbit, no, we fall out of orbit so quickly. We still have a little bit of aero drag. It's not much, but it's enough to cause the problem over long scales. And we actually would like to establish a research orbit where we can put up like the satellites that aren't dependent on their orbits, the non-imaging ones. These would be biological experiments, crystal growth, engineering experiments. we'd like to put those in a specific orbit so that we can fire repeatedly every day. We were talking about 3 times a day putting something into orbit in order to reach our goal of 1,000 missions. And this orbit would allow that because you have a lot of space. Even though you're going to the same orbit, there's a lot of space to go around that orbit, right? 4,000 miles, 3,000 miles in circumference. So you got a lot of space to put things in there. They don't stay very long. They start to drift downward. And nobody stays in this low Earth orbit. If you're going to put a satellite up, a communication or a weather satellite, they're way up in geosynchronous. They're real high up. So they don't experience this aero drag. So they don't fall out of orbit.
So there is no such thing as a regulation that you have to follow?
Oh, there's regulations. You better believe it. Space Command won't let you do anything without them. State Department won't let you do anything. FAA is our regulatory body, though. NASA is not. NASA is more of a prestige and a oversight than an actual regulatory body. So they've given the commands to the FAA. Flight worthiness or flight qualifications is probably the hardest thing at the moment because the FAA is not really. They don't really understand how to do a satellite or a launch system. So they're just getting their feet wet on it. Any other questions? Let's go. What do you guys get? What do you kids got? Come on. So this is one of the drones we got. This is not really a toy, but it's a $200 drone. It does 400 feet in the air. It's got 1080p camera on it, video streaming down to your cell phone. And I bought my 10-year-old daughter one of these for Christmas. Well, she's 11 now. To learn on.
My neighbor has one of those.
Yeah. Well, this is an interesting thing because we go hiking. We go hiking a lot. We go out gem mining, and we take our drones with us. So the technology that your parents want you to give up when you go hiking, guess what? You can con them into this because the videos are great. You can't get better video than flying over the canyons or flying through the forest, right?
So you said you weren't so like the little satellites you launch.
Yes.
They fall back.
Yes.
Are you worried about them coming and like smashing into Earth
Oh, no.
when they fall back?
They're coming in at between 17,000 and 18,000 miles an hour. These things are hitting the atmosphere and they're reaching degrees, 2,000, 3,000, 4,000 degrees. There's nothing left of them. When we talk about, when a rocket usually tells you that they destroy 99.9% of the rocket, that 0.1% is dust coming back down. Now, when we deorbited Skylab in the 70s, Australia actually charged us with littering because an oxygen tank landed in the outback and they had to remove it. When the Australians found out what it was, they wanted it back. So we do worry about parts hitting the ground, but if you do it correctly, like ours, the rocket itself, once it separates, actually goes into a tumble, and that tumble actually helps it break to pieces. And that's what a lot of these satellites, you'll hear deorbiting engines as a new catchphrase for the small satellite guys. They want us to require something this size to put a deorbiting engine on it so that we can purposely bring it down. Something this size doesn't need that. It's when you get into the 800, 900 pounds where you got titaniums and most of these are either plastics or aluminum or a lightweight material. It's when you get into the alloys, the rocket nozzle itself that's meant to survive thousands of degrees. That's probably one of the bigger ones that comes down, the tanks, the cryogenic tanks.
Wouldn't one of those plastic cubes coming down melt?
Yep, that's the point. We're coming through the atmosphere so quickly, so hot, that it just melts. Our actual wing, we call it a soft reentry because it's going to bounce off the atmosphere quite a few times and decelerate by bouncing off the atmosphere. So we don't accrue that huge amount of heat that you would hit by coming in at Mach 20. We're going to come in real slow and real long term. But yeah, most of that stuff melts. You know, you get up to 4,000 degrees, not much lasts. When you get balls of plasma surrounding you, you're pretty much done. Any questions? Come on, guys. Yeah.
Is that be related to the act where it's being talked about?
Say it again?
Is that be related to something you were talking about, or just something I just want to know?
I didn't understand it.
Does that be related to this?
No, what do you, ask your question.
If being pulled by, you're pulled like gravity, and you also somehow, if Earth pushes on you and you push on the Earth because of gravity, what's generating that push? Like,
So,
where's energy coming from? Energy is not supposed to come from nothing.
so that what gravity is not an actual energy. And if you get into the quantum, it doesn't exist. Okay, what you're seeing is the warping of space-time around the gravity around the object. So the example everybody gives is the rubber plane with the ball bearing on it, right? So you put that ball bearing on it, it pulls the rubber down like it would in a cloth, and that's the orbits. That's why you're orbiting. You're actually molding space-time around it. That's why black holes are real hard to get out of, right? It's not that it's actually giving out energy to pull you down. It's that it's just a hole, and it's pulling you through. What you got?
Would you try to use Boreas to explore black holes?
Black holes are real interesting because we don't really understand them as much as we think. Science fiction has kind of given us a good start, but we've never really actually observed one directly. We see after effects of them. The greatest thing that everybody doesn't know is there is stuff that comes out of a black hole. There's actual radiation that can come out of a black hole. So there's stuff that does not get trapped into a black hole. It's not an all-encompassing thing. And then on the flip side of that, there is a little theory out there called a white hole that actually ejects material out of it. And that's kind of an interesting, we've never seen one of those either. In fact, those are very unstable, but they apparently exist. The reason we do like the Large Hadron Collider is to start to understand those particles, because it's that subatomic particles that are coming out of that black hole. Why does that particle escape when another one doesn't? That's going to be interesting. I did like the visualization from Interstellar. There were some inaccuracies, but time dilation. You talk about time dilation in black holes, right? As you get closer to the black hole, as you get closer to the gravity well, as you go faster, time changes. The astronaut that was up on the space station for a year from his twin brother, he was, about a day younger? But yeah, time changes the faster you go, and black holes are notorious for that. One of the thought experiments was if light stops as you reach the event horizon, right? If you threw a dice into the event horizon, it should always hover right there on the event horizon. You should be able to look at the event horizon because the light is stopped, okay, because of the gravitation. That object should never view from your point of view, should never pass through that event horizon. The other one is, there's a great one. We know, science kind of doesn't like to say this, but we know what happened before the Big Bang. Okay, all physics breaks down, but we know an imbalance occurred before the Big Bang. Because if it was balanced, it would never change. So according to science, you can't know this because physics breaks down, but we do because the human mind tells you this. And that's the time thing also. That goes right straight to that time dilation that happens with the Big Bang. A billion years at the moment of the Big Bang, well, those particles were accelerating. So the time of a million years or a billion years is different.
How do you know where those 800, 900-pound rockets land? Like, how do you
We don't land them. We don't land them. We burn them up in the atmosphere. So we deploy our satellite into orbit, and then we put the rocket into a tumble, and it comes down into the atmosphere at high speed and basically breaks up and burns up in the atmosphere. It's part of the way we keep the costs down on the rocket, because if I had to return it home to like SpaceX does or Blue Origin, I'd have aerodynamic surfaces, I'd have flight computers, I'd have GPS computers, I'd have batteries, I'd have more propellant, I'd have a superstructure, and then there's a support structure to remanufacture the engine to reuse it again. So reusability, there's a big profit or big expenses you have to look at to make reusability a viable thing. And like I said, these payloads, they're not big enough. Most of the satellites in this payload class cost less than $100,000 to make. You're going to charge them $5 million to launch it. We'd like to get down to that, about the same cost of the launch as the same cost of the satellite, right? And we think this will become a commodity. So you'll eventually get to a point where, you know, whoever's got the cheapest launcher you're going to go to. Right now you can pretty much dictate your prices within ranges. So
if you just burn the satellite in the atmosphere, how do you collect the data?
we do downlinks. So as it passes over your head, you got about 3 seconds, okay, at the speeds we're traveling, at the distance which we're traveling, from horizon to horizon. Okay, we can usually get downloads. There is a couple networks around the world that'll give you constant downloads. You have to pay them to use their antennas, and they got stations around the world. Deep Space Network is NASA's version, okay? But if you're gonna track it yourself, the thing is moving so quickly. So you get about a quarter of your bandwidth here, you get full bandwidth, and then a quarter of your bandwidth down to the horizon. And that usually takes about 3 seconds from horizon to horizon. So you can see it's fast, right? We're really cooking here. So those downlinks, that's why you'll hear NASA, even when NASA does it from like Jupiter or Pluto or Saturn, you'll hear them say we're gonna start a downlink. It's because the satellite's in its position in order to downlink data on a reliable basis. You're on the backside of the planet, you're not gonna be downlinking data.
So it's only going to be there for like a certain amount of time, that optimal position?
Yeah, yeah. And every time you try to move, every time you repoint your antenna, you're using propellant. So you're killing the lifespan of the spacecraft. So you're better off waiting for that downlink time to come around in order to do your downlinks.
Thank you.
Not a problem. Do you have a question, ma'am?
Well, you answered part of it, but I was wondering, why do you want to send all these up there? Isn't there enough things going around the Earth that you can collect data that you need?
No.
What are you finding that's different?
Osteoporosis. The experiment that just went up to the ISS is a bone loss experiment, because astronauts have a huge problem with bone loss. So they put on a bone densitometer up there. Well, it doesn't need to be up there all the time, okay, keeping it on the space station. But some of the pharmaceutical companies, in order to get very pure drugs and very new compounds, they'll put experiments up there, and it'll change the way they develop drugs. The biologicals, growing in space has changed the way hydroponics is done. So they actually were growing things under certain spectrums of light, and that spectrum of light actually produced better crops. So then they could produce better grow houses and everything. There is never going to be enough stuff up there. Literally, I can think of a million things in every industry that's going to benefit. Agricultural. So you want to know what your crop yields are so you don't have famine. We can go up there, we can put it up a couple months before your harvest season, and now we know exactly what your crop yields are. Your waste management, every year they have to monitor the landfills. We can put a satellite up there and monitor all of them in one sweep. And those are just commercial applications. That isn't even the science applications behind it. I'm a commercial guy, so I'm always looking to make money. And there's a lot of money to be made. Your first trillionaire, kids, is going to come from the space industry. Think about that for a second. First trillionaire that brings back one of those asteroids Yeah, you'll never be able to touch them. Put a whole government out of business if he wants. Yes, ma'am.
So how long do these satellites stay up?
Anywhere from a month to 2 weeks to a month or two in this payload class. Once you start adding propellant tanks and once you start going to larger orbits, then you can stay up almost indefinitely until you run out of battery or it breaks down. In fact, there's a whole orbit out there called Graveyard Orbit, where they basically park all these dead satellites. And I think it's Rocket Aerodyne is going to go and grab one of them, fuel it back up, and put it back into service. And that's actually a plan that's in works for a couple different companies. So even if the satellite goes dead, we're getting to the point where we can go up, do the maintenance on it, and bring it back into service.
You mentioned a $150 3D printer.
Yes.
What is that?
It's a Prusa i3. They come in kits. It did take me 20 to 50 hours to get it working to produce a rocket nozzle. Took me about 20 hours to get to produce the toys. It's a very common design. It uses a Raspberry Pi. It's a kit you put together. You install the firmware. All the instructions are there online. And then the rolls of filament are about $20 a roll. You can get them at Micro Center. One of these, let's see, 4 of these come off of one roll. Those globes probably 20 coming off of one roll for $20. Yeah, the printers themselves, get it off of like an Amazon or something like that. Mine, I bought the cheapest one I could get because I wanted to do it on the cheapest one I could get. So mine's actually run by my computer. But some of them out there have their own computer system so you can run them on their own. The kids, there's a lot of 3D printing software out there, or 3D CAD type software out there that allows them to actually make their own models and everything. Otherwise, you can go up on these websites and download other people's designs. I didn't model the Millennium Falcon here. Okay, I didn't model this, the xenomorph head from Aliens. Okay, this was somebody else. They put it up there for free. You download it, you print it out. Somebody stole my baby Groot. I have a baby Groot that I print out. Actually, I've made 5 of them now because that was the exact reaction I get from everyone is, oh. So I keep having to give them out. I make useful things. This is a locking collar for a rocket separation. So one side of the collar is at 50% infill. These are not solid pieces of plastic. They're hollow inside, and depending on the infill, we can make the strength of it. So the back side's only 10% infill. So when this goes to break, the back side's always going to break first versus the front side. That's the type of thing. This is a little wing for our drone. And like I said, afterwards, you guys can come up here and play with anything on here. Don't touch the drone, this drone. I just fixed it. I crashed it the other day. This we could take to the wind tunnel, finish it out correctly, take it to the wind tunnel, and do our stress tests on it. This took literally about 2 hours to print. If you had done this, you would have had to, back in the day, you would have had to make a balsa wood model, and then you would have had to lacquer it and glue it together, and then you could put it in the wind tunnel. In 2 hours, I could have put this thing in the wind tunnel and got my data off of it. So these are tools. I said it's quickening your ability, kids, to actually make something. Okay, and that's what I love about being an engineer is I get to make stuff. Anything I want. The 3D printer, I get to make whatever I want. If I want another baby Groot to put as a hood ornament on my car, go for it. My daughter came in. She was 8, and she goes, the boys are outside and they're playing guns and I want a toy gun. I said, good. We went down to the 3D printer and we printed out Han Solo's blaster. So about 3 hours later, she comes running out with Han Solo's blaster, and now all the boys want Han Solo's blaster.
I want Han Solo's blaster.
Yeah. My nephew stole, if you guys know Firefly, my nephew stole my gun from Firefly. So, you know, because he had to have it. So I'll be here for a little while afterwards.